Today's lesson is on surface integrals, and just like line integrals, there are two types of surface integrals. There's a surface integral of a function, and there are surface integrals of vector fields. And this lesson specifically, we're just going to go over surface integrals of functions. All right, so a couple things that we need. So we need to recall some formulas for surface area. So when we looked at surface area, there were two different ways that we can describe a surface. So if our surface is given, if we are given the surface as some z equals a function of xy, then the surface area can be calculated with a double integral of the square root of the partial of the function with respect to x squared plus the partial of the function with respect to y squared plus, I'm running out of room, 1. That's all underneath the square root there. So that's one way to calculate surface area. If we were given a vector description for the surface, and also remember that if we describe a surface with a vector, with a parameterization, we need two variables in it. So if we describe it with a vector with some x component, a y component, and a z component, and those three components would all have to be in terms of u and v, then the surface area would be calculated by taking a double integral of the magnitude of the cross product of the derivatives of the vector. So this is a magnitude, a magnitude of the vector, and it's a magnitude of the cross product of the derivative with respect to u and derivative with respect to v of the description of the surface. And that's how we would calculate the surface area. Okay, so now keep that in mind, and when we go to find the surface area or the surface integral calculation, there's also going to be two different kinds depending on what our surface looks like. All right, so this is just for a surface integral of a function. So surface integral of a function. So if we are given the surface description with a z equal to some function of xy, then our surface integral, which is a double integral over a surface of some function of x, y, and z, we could calculate this by taking a double integral over a region D of the function of x, y. Oh, do you know what? I need to use a different function here. I have two f's going on, and that's a little confusing. So let me back up, and let's call this function, it's the z, let's call that g instead of f. Okay, so then our function would be a function of x, y, and then for z we'd have to plug in that function g. So we would make our function all in terms of x and y, and then we would have to multiply that by the surface area calculation. So by the square root of the partial of g with respect to x, square it, plus the partial of g with respect to y. So that is a g on top there. And square it plus 1. And then at the very end here, let's include a little dA in there. And dA is going right in the end there. All right, so what this surface integral now is representing, we have a function that we are integrating over a certain area of surface. So that area of surface is right here. And D is going to be what kind of the image of the surface would look like on the XY plane. So because we're given that Z equals, D is the image on the XY plane. Okay, that's one type. The second type, if we are given our surface as a parameterization, so if we're given a vector valued function for that surface, it would have to be in terms of two variables, then our integral of a function over a surface would be, we could find this by taking a double integral, again over d. D is going to be that same image on the xy plane of the function evaluated at r sub u cross r. I'm sorry, that is not quite right. Let's try this again. The function is evaluated at r, meaning you're going to plug in x, y, and z into the function, and then multiply it by the magnitude of r sub u cross r sub v dA. Once again, in this one, we have our surface area, and we're integrating a function over that surface area. Okay, so let's do an example of this. So let's find the surface integral. So we are going to find the surface integral, the double integral over S of yz ds. Now be very careful here with the notation. ds versus dA mean very different things. dA just means integrate over an area. So if it were an A right there, it would mean integrate over an area. But because this has an S, it means we have to integrate over a surface, and we have to use our formulas to do that. So we're going to find the surface integral. If S is the plane x plus y plus z equals 1 in the first quadrant. Okay, so this is a surface integral of a function. We have a function right there. And we are given an equation for it. And so we want to use the fact that z is equal to 1 minus x minus y. This will be our function g that we talked about in the formula of that on that last page. Right, so this will equal our g of x, y. All right, so this plane what the plane looks like is it has an intercept of 1 on the x, the y, and the z. So the plane itself looks something like that. If we are to project that, find its shadow on the xy plane, that would be where, that would be the part kind of right down here, just on the XY plane. And that part is right, if we, that's where it crosses the X and the Y right at 1. That's this area. So that's going to be the D from our formula. Okay, so I think we're ready to plug everything in. Oh, maybe not yet. I think we need to find the equation of this line or this line, in order to set up our integral. So that line is where z is equal to 0, and where z is equal to 0, that is where x plus y equals 1, and so that line is where y equals 1 minus x. Okay, so now let's plug everything in. So for our surface integral, we will have a double integral of y. I'm looking at this function right now. So a double integral of y. Z is given by the function 1 minus x minus y, so I'm going to plug that in there. Maybe if I can write it correctly. All right, so that is 1 minus x minus y. And then we have to multiply that by the square root of the partial of z with respect to x. The partial of z with respect to x is negative 1. We're going to square that. The partial of z with respect to y is negative 1, and we're going to square that. And then we add 1. Adding 1, that's in the formula for the surface area. Okay, so now that we have that part, we can look at the bounds. Now for the bounds, we're going to go back to what we did for a double integral. We're going to look at the xy plane for those bounds. I think we could do this either going dx dy or dy dx. My intuition is because we have a y equals, I would use that. And I would use that as a top function for that shape. So I would use that y equals on the top of the first integral, and I would start with dy. Then y equals 0. So y equals 0 would be the bottom. Y equals 1 minus x would be the top of it there. Then just looking at the numbers for x for the outside of this integral, the numbers for x on the outside of this integral is going to go from 0 to 1. All right, so if we simplify a little bit, integral from 0 to 1, the integral from 0 to 1 minus x. In order to integrate, we'd have to multiply through by y, so this would be y minus xy minus y squared. We've got a 1 squared, a 1 squared, and a 1, so this whole thing would be root 3. Let's stick that out in front. dy dx. And at this point, you guys know how to integrate a double integral. If you want to carry through the calculation on this, so if you carried this through, so dot, dot, dot right there, you would end up getting root 3 over 24. So just in case you can't stand that I'm not going to finish this integral, we're just going to set it up. If you want to solve it, you would get root 3 over 24. All right, so there's an example of finding a surface integral over a function. And maybe we should take the time to actually do this exact same one, but do it with the cross product. That would be a good thing to do. Let's do that. Okay, so let's find the surface integral. So we're going to find the surface integral. It's the same one. Let's do the same one here, just so we can see that we would get the same thing. Y times 1 minus x minus y. Whoops, I just plugged that into the... Let's back up just a second, I'm sorry. That is y times z. Y times z ds. And s was the plane x plus y plus z equals 1. All right, so now if we're going to use the other formula, really we would need a vector parameterization for this surface. So what we need to find for that surface is an x equals, a y equals, and a z equals, all in terms of two variables. Two variables for a surface. Remember, it's one variable for curve, two variables for surface. Now because z is equal to 1 minus x minus y, I could use x equals x and y equals y. So my two variables are an x and a y. And now I've got an x, y, and a z all in terms of those two variables. All right, so my r is going to be x, y, and then 1 minus x minus y. So in order to do this with that r, we would need to find the partial of r with respect to x. That would be 1, 0, negative 1, partial with respect to x. We'd need to find the partial with respect to y. There's no y in that x component, so 0. The derivative of y is 1, and the derivative in this next part, with the y, that would also be negative 1. Now the cross product of these two, so r sub x cross r sub y, the x component of it is going to be 0 minus a negative 1, so that'll give us 1. Y component of a cross product is always negative. It's going to be 1 times negative 1 minus 0, so that would be minus a negative 1. And then the z component of it would be 1 times 1 minus 0, so again 1. The magnitude of this vector is the square root of all the components squared. 1 squared plus 1 squared plus 1 squared, and we get that root 3, just like we did before. So now, plugging all of that into the formula that we have, it told us to take a double integral of the function evaluated at r. The function evaluated at r. And what this means is take your function, that was your function, and plug in x, y, and z from your r. So we take our function, y was y, z is, so y is y, it's right there, z is 1 minus x minus y, 1 minus x minus y. We multiply that by the magnitude of the cross product, where we got root 3. There's that root 3. And then we have the exact same double integral to look at, so we have the exact same bounds as before. So we'd still have to look at that xy plane, that line where y was equal to 1 minus x. And so we would integrate from 0 to 1 minus x. X would go from 0 to 1. And we have the exact same integral that we had on the page before. All right, so there's our two different types. So remember, there are themselves two different types of surface integrals: a function and a vector field. All we've looked at right now is functions. And within the functions, we have to determine whether our surface is a z equals surface, and whether we want to use that was the first example, or whether our surface is given with a parametric equations, and then we would use a different formula for that. All right, so in the next video, we'll look at surface integrals of vector fields.